Welcome to the UCL Institute for Environmental Design and Engineering Integrated Building Design webinar. My name is Chen Peng. I am a PhD student at IEDE. At IEDE, our teaching and research tackles some of the greatest and the most complex issues facing our built environment. This webinar series explores how buildings can adapt to some of the challenges and changes we faced in the 21st century, such as climate change, resource efficiency, health, and well-being. Today's webinar, we will discuss the Beecroft Building, a world-class research facility recently constructed for the Oxford University Department of Physics. Before we start, there are two things that I would like to mention. Today's webinar will be recorded. The recordings will be available afterwards on demand. And there will be a Q&A session after the presentation. Please feel free to post any questions by using the Q&A function at the bottom of your screen. So I would like to briefly introduce our speakers now. Today we are delighted to be joined by Rebecca Folt. She joined the Hawkins and Brown 7 years ago. She has developed a specialty for higher education design, particularly for research facilities that requires technical sophistication and collaborative design sensibilities. She was a project architect on the award-winning Beecroft Building. With a passion for good design, she strives for the best and the most creative solutions for all design challenges. And we're also joined by Nick Lawrence. Nick is a chartered engineer who has worked in building services for over 15 years. He's working at Relied for the last 7 years and specializing in the science and research sector. He's currently working as the lead mechanical engineer for the Life and Mine Building, which is Oxford University's largest ever project. So without further ado, I would like to hand over to our speakers.
Thank you, Cheng Peng. That's great. We're really excited to be here and to be able to tell you and share with you this fantastic project. So we're going to dive straight in. And the project really started with Professor John Wheater. He was the head of the Department of Physics at the University of Oxford at the time of the project. And he came up with a very clear vision for the Beecroft Building. And that was that it would become a beacon for leading physicists across the world, and that it would provide world-class high-specification labs that would allow research at Oxford to advance into a new realm. So this is some of images of some of their existing facilities that they were using and occupying before the Beecroft Building existed, and that sort of reinforces very clearly their need for a new building. So they were occupying converted terraces that were obviously not suitable for undertaking high precision experiments at all. So you can see this image in the middle is shows some of the laboratories that were just shoehorned into sort of inadequate spaces. And then the offices were also very cellular and sort of buried away across a warren of corridors. So it was completely not facilitating collaborative working, which was a huge issue. So there was essentially three key components to the brief. So one was to combine two specific research groups within the physics department, which was the theoretical physicists and the experimental physicists. And we're going to talk about that in more detail later, but they have very different requirements. But the brief was essentially to provide a collaborative environment that would bring those two departments together. Then secondly, the building would also need to provide a strong connection back to the science area within which the building is located, and also back to the existing physics department, which occupies other adjacent buildings. And then thirdly, the building needed to provide a series of high-spec labs, which would allow for world-class research to be undertaken. So the project site is along Parks Road, and it's very prominently located at the entrance to the science area. So this here is the science area of the university. And you can see this group of buildings here is already occupied by the physics department. So they're spread out across a series of buildings. And the Beecroft Building essentially is located here, which completes that physics complex. So it was developed on the last remaining vacant piece of land that the department and the university have available. And the project was also located in a very historically sensitive context. So the site was constrained on all four sides. So by existing buildings on the east, the university parks, which is also a conservation area on the north, Parks Road to the west, and then a protected cedar tree to the south. And there's also a number of listed buildings in the neighborhood, and most importantly, probably the Keble College Chapel, which sits opposite the Beecroft Building and is grade 1 listed. So this is just a view across Parks Road at the site. So before the Beecroft Building was built, it was a surface car park. So the park is to the left here, and these two buildings that we're looking at in the background are part of the existing physics complex. And then this is just looking back the other way at the listed Keble College Chapel across the site. So this is the final building. And so the building form and its materials were essentially designed based on the surrounding context. So the facade palette combines a combination of different materials. So the fin system is a copper alloy, and it actually weathers naturally to develop a very sort of dark brown, bronze looking finish. And then behind that is a curtain wall system, which combines clear glazing with solid black spandrel and an interlayer of expanded copper mesh glazing. And so the combination of material colors and the sort of vertical emphasis and pattern of the facade really was to reflect the Gothic style of Keble College Chapel, which you can see in that top left image. And then this is a view from the south. So that tree in the right-hand side is a protected cedar tree. So as part of the project, there was a new forecourt completed with some landscaping that essentially ties into the more public science area context. And you can also see we included something called a picture window on each of the facades, which essentially is where the social spaces penetrate against the facade, and these provide and frame views out of the building to frame certain important parts of the context. So this view here frames the cedar tree to the south. There's a picture window on the west, which looks out at Keble College, and one on the north that looks out across the parks. So the building organization is fundamentally driven by the different briefing requirements that the two departments have. So the technical laboratories are buried below ground because that is where they can utilize the inherently stable ground conditions and the dark spaces. And then that allows for the theoretical offices and social spaces to benefit from daylighting and views out on the upper levels. And then we have a collaborative atrium that extends throughout the building and stretches down into the lab floors to provide that connectivity. Because of the very highly serviced nature of the labs, you can see that despite it being a 5-story basement, there is only 2 usable lab floors because each laboratory floor required a dedicated service floor above for the distribution of pipe work and duct work. And then the lowest lab floor also required a dedicated floor below to accommodate vibration isolation equipment. But we'll go into that in a bit more detail later. But essentially this resulted in the deepest basement in Oxford, which is 16 meters deep, and it's actually deeper than the building is tall. So some people actually call it the iceberg building. So this is just a typical lab floor. So you can see it's a very efficient layout, obviously, to make the most use from a technical perspective. And we've included a circular corridor arrangement to avoid dead ends and improve user circulation and interaction. And then this is the ground floor plan. So as part of the project, we designed a new shared reception. So this link structure here is a shared reception for the whole physics department. So we've essentially designed a new front door, which you approach through the new landscaping that you just saw in the image from the south. And then the remaining part of the ground floor is primarily taken up by plant and back of house facilities, with some seminar and meeting facilities overlooking the new quad. And then a typical upper floor plan. So we've got the collaborative atrium in the center with a ring of offices around the outside. And we've got further connections back to the existing physics department on these upper levels via link bridges as well. So looking at the theoretical physics component, so theoretical physicists essentially work in offices. So they're based in an office where they develop and derive physical formulas and concepts. And these ideas are then tested by the experimental physicists in the laboratories. And then these results and findings are, fed back to the theorists who then further develop those ideas. So they need to work collaboratively with the experimental physicists, but they also need sort of very quiet thinking spaces. And this picture here of Albert Einstein might look very old, but actually if you removed him from the image, this could totally be a photograph from the current Beecroft Building, because blackboards are still a key requirement and a key tool that theoretical physicists use to develop their work. So it was a key part of the brief on this project. So every collaboration space and office had to contain full height blackboards. And similarly to how designers are very specific about the types of pens and paper they like, the blackboard surface couldn't just be any blackboard. So we had to test quite a lot of material samples with the client until we got to a point where everyone was happy with the product that was selected. So to summarize, the challenges that we faced in the on the theoretical part of the program, which is those above ground floor levels, was really to provide a collaborative environment whilst also providing sort of more isolated, silent thinking spaces, and to balance that visual connectivity that you want to promote collaboration with acoustic separation. So there's a few key design moves that concepts that we implemented to make that a success. One of the first was just clearly zoning our floor plan. So as discussed before, we've got the collaborative core in the center with then the acoustically isolated offices around the perimeter. We then also designed the circulation in a way that we encouraged all main circulation to occur through the atrium space. So we've got a set of meandering stairs through the atrium void and tucked the escape stairs away from sort of immediate visibility and access to really encourage people to use that atrium and to sort of maximize chance encounters and so on. So this here is an image of the completed building. So this is as you enter the atrium at ground floor level. So you're immediately drawn up into that social space via this social auditorium stair. And you immediately also get these visual connections across all floors and platforms of the social core. And then this is a view down, just showing these meandering stairways that sort of wrap around the center of the atrium void. And then another component was the introduction of these collaboration platforms. So they're located at half levels within the atrium void. And the idea here was to, by locating them in between the floor levels, they wouldn't be sort of associated with a particular floor and would just sort of be more accessible and open to all building users essentially. And the design or the idea behind these is really to expose the discussions and conversations in these breakout spaces to the wider building occupancy, in an attempt to encourage unobvious collaborations just by overseeing and overhearing what other people are talking about. So this is some images of the completed atrium. So on the left-hand side, you can see that each of the platforms is based around a full height curved blackboard. And on the right side, you can see 2 of the platforms. So we have 4, 1 in each corner of the atrium, to make sure that each platform benefits from the daylighting and sky views from the roof light above. And yeah, the sort of big blackboards really help with, you know, allowing people to oversee some of the work and ideas that are being explored, and to encourage them to join in as they're sort of moving through the atrium. And then the 2, I guess, key design components that you used to separate, that we needed to include, was walls and the balustrade. So again, in order to maximize visual links, we designed the balustrade purposefully as a slatted fin arrangement to allow for visual links through them. But also at the same time, that slatted balustrade provides a sense of enclosure to, in particular, the platform breakout spaces that we were just looking at. And then we also introduced something called a staggered glaze screen. So these 2, you can see that in this arrangement here. Essentially what they do is they provide acoustic attenuation between breakout spaces that are sort of adjacent to each other, but it still allows for that physical connectivity, because we didn't want to put sort of doors and enclosures on each of the breakout spaces. And we wanted to keep them open so that, again, you can overhear and, you know, join into conversations that are happening. So this is an example of that staggered screen arrangement. And then, yeah, with the breakout platform in the foreground. And I'm going to hand over to Nick now, who's going to talk about the more of the experimental physics brief.
Thank you, Rebecca. Yeah, so as mentioned, the basement levels were where we had the experimental physics laboratories. And that is where, you know, experiments are carried out, and some of the theories are tested, and yeah, very sort of physical work in laboratory space. So the sort of two main areas of research that the department were going to use this building to develop are the development of quantum computers, and also scanning at a very, very high resolution. So each one of those research elements had its own unique challenges. So the quantum computers require incredibly stable environmental conditions, and the high resolution scanning requires incredibly tight vibration standards, and we'll just come on to the reason behind that a bit now. So this is a typical basement floor plate, and we had essentially the quantum computer laboratories are in the middle, and then the scanning rooms around the perimeter. So sort of quite close vicinity to each other, and those are the 2 main laboratory types. And yeah, we'll just come on to that now. So quantum computers, for anyone who doesn't know what they are, probably most of you don't, they're different to normal computers. So normal computers have bits, and the bits are arranged as a 1 or a 0, and that is how the computer processes information, by putting those 1s and 0s into a different order. So a quantum computer contains qubits instead, and the qubit can be a 1 or a 0, or like a superposition between the 2. So each qubit essentially has a vast sort of superior knowledge, data storage compared to a normal bit. And so if you make a whole computer's worth of qubits, then the sort of processing speed and the data storage is potentially a lot greater. So that's what the department are developing, and their vision is that in sort of 20 years time we'll all be using quantum computers. So they're really keen to develop that technology. But it's, so what they're doing in there is a qubit is made up physically of an ion, and just to put it into context, an ion is a nanometer in size, which is 1 billionth of a meter. And like a human hair, you can see there is approximately 100,000 nanometers big. So just that puts it into context of how atomic and molecular this is. So what they do to develop these qubits is they put them in an ion trap, and then they beam an optical laser at it, and they induce a reaction, and that's how they sort of impose information onto it. And so because it's so atomic and molecular, it's very it needs to be in an incredibly stable condition, because any changes in environment can cause the experiment to misalign. So one thing that they said was in their current building stock, you saw some photos of earlier, basically they spent about 80% of their time realigning experiments and only 20% actually able to do any research. And so in the new building, they wanted to, flip that around so they could spend 80% of their time doing research and only 20% realigning experiments. So the brief was, the most sort of tight environmental control they could think of. So they actually requested that at 0.1 degrees temperature control to 0.1 degrees, so 0.1 of a degree at the actual experiment. And in the room itself, they wanted temperature control to 0.5 degree, and they wanted relative humidity to be controlled to 10%. So yeah, very tight environmental control that we hadn't worked to before. So this is typically how this is some photos from their existing buildings before we finished Beecroft, and this is typically how they arrange those optical experiments. So they put the ion trap and the lasers on a table, and then they typically will put an enclosure around the table, and the main purpose for that is just to try and keep the environmental conditions at the experiment quite as close as possible, and also just saves them having to over air condition the whole room when it's just that one area they want to keep stable. So they did say that it's actually at the experiment is where it's critical to have the temperature control. They weren't really that bothered about the 0.5 degrees C temperature swing in the lab, as long as they had temperature stability at the enclosure. But they didn't want an oscillation in temperature in the lab causing an oscillation in temperature in at the experiment. So this is a sort of a floor plan, and because of the vibration control, which we'll come on to in a bit, we actually needed to keep all rotating plant outside of the general lab area. So we had a consolidated single air handling unit in the plant room, and then like a network of ducts from that plant room, which Rebecca already mentioned. There was like a walk-on floor above each of the laboratory levels, and that was just to house the sort of size of ducting that we needed and the pipework that we needed to then go to each one of these labs. So the general design strategy was to maintain such sort of stable conditions at the experimental enclosure. We were just basically going to just sweep it through with air. So we designed quite a high air volume to go to that experimental box, roughly 80 air changes an hour. And we were just going to have a very, very close control air conditioning system that was just going to maintain the air going to that enclosure a very stable condition. And so we just felt that washing that space with air at a very stable condition would maintain that enclosure at very stable condition. And then the room itself, because there would be people and equipment in there, that room would generate heat, and so the air going to the room would vary depending on how much heat was being gained in the room at the time. So we had two separate branches from the ventilation system going to each lab, one going to the enclosure, and that would just be a constant temperature, and then one going to the room that would be a varying temperature depending on what's going on in the room at the time. So because this was quite new, that we hadn't designed this type of system before and weren't aware of many buildings that were achieving plus or minus 0.1, the project took the decision to build a mock-up to basically test the design solution before we built it on site. So we did this in a warehouse. This is a photo of the mock-up that we built in. This is built in a warehouse nearby that was the client provided. And the client also provided the actual laser table enclosure that you can see there on the left, which was the same specification was going to be provided on the project. And essentially what we wanted to test was, the sort of strategy I just explained of if we sort of wash that environmental box with air at a very stable condition, will we maintain that very stable condition in the box itself? So we built this mock-up. And on the next slide, you can sort of see we basically just positioned a number of temperature sensors. So we gave them all a number, so temperature T1 to T5 basically, and we were just going to monitor exactly what was going on at each point of the system. And then the key thing really was that we would achieve the stable condition at T5, which is a temperature sensor actually within the enclosure. So we did a first round of testing, and it was pretty unsuccessful actually. You can see the different colors represent different temperature sensors, and you can see there's some pretty significant oscillations in temperature, swinging around, you know, beyond a degree, so well beyond the brief of plus or minus 0.1. So we looked at what was not quite right about it, and one of the key things we found was that we weren't getting very good mix of temperature in the air. We were getting different temperatures at different points in the system, and we felt that was because the heater battery we provided wasn't delivering a uniform amount of temperature into the airstream. So you can see the photo on the sort of left hand side. We had this sort of quite crude probe type heat battery, which wasn't delivering uniform heat into the airstream. So we changed that with a new coil, which was a bit more advanced, had a bigger coil, much more spread around the duct and the airstream, so it would deliver a more uniform amount of heat into the duct. And also we increased the duct size, the coil's output size, because the system was struggling really to do what we wanted it to do. Another thing we found was that we had the temperature sensor T2 on the previous slide as the controlling sensor, but because it was like within an enclosed duct, it was responding too quickly to any changes in system temperature. So that was causing the system to oscillate very quickly. So we changed the controlling sensor to be a sensor actually within the enclosure. And then another thing we found, as again, I already mentioned, we were finding different temperatures at different points in the system and at different points in the enclosure. And we felt that was because the ducting design wasn't lending itself to have like the air mixing before we were distributing it to the two grills. So basically we modified the duct arrangement so that it was basically, we gave the main sort of single duct maximum time for the air to mix before we separated it out to the two grills. So those are all the sort of changes we made on the mock-up, and then we did some more tests, and actually, yeah, we did see a real improvement. So the red line symbolizes the temperature in the warehouse. So we did a couple of like shock tests to where we controlled the temperature in the warehouse by turning some heaters on, and that varied the temperature going into the system. But you can see when that occurred, there wasn't any sort of big oscillation in the temperature within the enclosure. So the system was basically able to deal with any impact of a change in air temperature on. So basically, effectively, we were able to achieve the temperature control we required, plus or minus 0.1, with the system following those modifications. And so it was a real success story, and it was brilliant that we'd done that on a mock-up, because it then meant we could feed those lessons we learned into the design. So yeah, this is just an image from the top image is from the model that we built, and you can see that that's just replicating the second ducting arrangement. So we made sure, you know, we only bent the duct to the two separate grills at the very latest point that we could. And also, this is the set below image is an image of the schematic for the system, and you can just see we've got the 2 number heater batteries that we added in, and the temperature sensor in the right place, as lessons learned from the mock-up. And so that meant that the project was quite a success, really. You know, if we'd learned those lessons after we'd built all of the labs, it would have been a real difficult obstacle to overcome at such a late stage in the project. But you know, because we learnt those lessons in time to feed them into the main project, the testing and commissioning of the final systems went very smoothly, and was a real success, and meant the project finished on time. So one thing we did on this project that was different to what you might do on normal projects is over and above the sort of normal commissioning and testing that you do with the building empty, we simulated some like in-use heat demands to sort of prove that the system could deal with a real life experiment, but before the department had moved in, so that we had time to rectify anything that was found to be wrong. So on the image on the left, you can see we put some tubular heaters in the room, and we basically simulated like put those in the same place where scientists were saying they would put heat emitting equipment, so we could simulate an in-use heat demand, and then we turned the system on, and we turned on heaters off and on, and then we did the same in the lab next door, and then we did the same in the lab next door after that, and we just monitored each lab and whether it was able to perform. And again, that was a real success, and we found when we were doing that testing that we were able to achieve the tight temperature control needed. In fact, we did sort of better than the brief, actually. You can see there we were able to remain within plus or minus 0.5 of a degree, so a 20th of a degree centigrade. So yeah, really tight, stable environmental control. So here's just some images of the final building. So on the left is a laser lab upon completion, and then on the right you can see that's once some of the research groups have moved in and set an experiment up, and yeah, are developing the next generation of computers. Yeah, so the other type of research they wanted to do in this building, as I mentioned, was very high resolution scanning, and this is something called atomic force microscopy. And basically what they do is they scan surfaces at an incredibly atomic scale, and the way they do that is effectively they take like a needle, not a million miles away from a needle you have on a record player, and they basically drag it across a surface, and every time that probe goes up and down, you know, it records its movements and generates an image of the surface it's scanning, and so because it's so atomic and molecular, you know, they need very stable vibration control. They did say when we were doing the original briefing that they were able to tell when a train was going by an Oxford train station, which is about a mile away, and they could tell, you know, that was happening because it was picking that up, just the vibration. And basically they only did their most critical experiments in the dead of night. They were literally doing them at like 2 in the morning just to have you know, the most stable environment they could. And so again, the brief was really demanding. They requested at the experiment where the microscope actually is, they wanted VCM. So VCM, these are vibration curves, and they're essentially like theoretical levels of vibration that have been developed by theoretical physicists, essentially. And you can see operating theatre is sort of one line above VCA, so that's, you know, very stable amounts of vibration, and so VCM is right down there. And actually at the time of designing the building, some people said like VCM wasn't even physically possible. It was just a theoretical amount of vibration control that couldn't actually be achieved. So it was a really they really wanted to push the boundaries of what they could do. So I this was more of an architecturally led solution. So I sort of pass back to Rebecca to talk through how we manage that solution.
Thank you, Nick. So yeah, the key challenge, there was 3 key challenges really that we faced on the experimental side of the brief. And as Nick was alluding to achieve that level of vibration isolation, you would ideally build this building on a greenfield site in the middle of nowhere, away from any external influences. But we were designing a building that was located in the centre of Oxford, right next to a busy road with sightseeing buses, etc. So that was a huge challenge. Secondly, we then had the conflicting criteria requirement for tight environmental control, which Nick already talked about. And to achieve that level of environmental control, you need a lot of vibrating and moving equipment. So that obviously, again, is sort of going against the provision of a very stable lab environment. And then thirdly, there were no reference projects that combined these 2 criteria in any way. And even just achieving VCM, as Nick was saying, was sort of under discussion whether that was actually possible and had been achieved anywhere. So we were really sort of you know, having to push the boundaries here. So one key, I'd say actually probably the biggest component, the most important component as to how we achieved this was actually collaboration. So this type of design performance was beyond any one single consultant's scope and expertise. So the structural engineer alone could not have, you know, designed the structure to create this, to achieve this level of performance. So we had to make sure that across the full design, client, and contractor team, we really fostered a very open and creative environment, one that actually sort of, allowed for creative and innovative thinking. So it was really a sort of forum where no questions could be stupid questions. You kind of really had to put yourself out there and not be afraid to suggest something, possibly impossible. That was sort of the whole premise of this collaboration, I think. And then secondly, we also had to develop our own bespoke design tools. So in order to simulate the vibration performance, we actually got in a vibration consultant, and he is actually himself a researcher at Southampton University, who's essentially, treating this as a research project because it's not sort of a service he usually offers. But so we integrated him into the team, and he did something called a finite element model, which is a screenshot on the left side, which essentially means he took the structural design, the Revit model that the design team had produced, and started to input any vibration influences. So we went to site and actually measured existing vibration levels on the site. And then he also input vibration data from the MEP systems that Nick and his team designed. And then he also had to factor in impact vibration from footfall from people walking around the floor plates. So taking all that information, he would then simulate how the structure would behave, and as a result, what level of stability and vibration isolation the structure would perform at on different parts of each floor plate. And this was directly used as a design tool to revise the structural design, and as a result, the architectural design, because we had to stiffen up the whole structure quite significantly just to provide a sufficiently stable baseline structure to work from. So our floor slabs on the 2 basement levels, as you can see on the right side here, they actually came up to almost 600 mil thick, which is very thick. The lowest raft slab was actually 1.2 meters thick. And we also had to increase the size of columns and introduce additional shear walls and columns that were, above and beyond sort of structural requirements, just to stiffen up the fundamental design. And sorry, before I move on, actually, we, similarly to what Nick was describing about the environmental control, we had to make sure that the performance of the building was validated as the building was constructed, because if the building had not met this level of vibration isolation, the client would have not accepted the building. So it was a huge risk to the design team and the contractor to commit to providing this level of performance. So again, with the vibration consultant, we worked together to develop a bespoke method of testing and verifying the design as the building was built. And that translated to essentially stopping all construction and measuring the vibration performance of the structure at key milestones of construction. So following completion of the superstructure, then following installation of interior walls, then MEP system. So we did it stage by stage to make sure that any misalignments in performance could be picked up and then reviewed and dealt with early on. Luckily, none of that happened. But that was just a sort of measure of security that had to be allowed for. So again, in terms of design, there was a few sort of fundamental principles that we followed to support achieving that level of performance. So we zoned the floor plates in a sense that, so Nick already talked about that all plant was consolidated into these plant rooms in the top left corner. And they were then actually also physically separated from the main building structure by means of this movement joint where you see that orange line. So all the ductwork and pipework that transferred from that plant room onto the main floor had flexible connections at that point to again minimize any transfer in vibration. And then we also zoned the floor plates so the most sensitive, vibration sensitive spaces were furthest away from the plant itself. And then it sort of very quickly became clear that to achieve VCM, there needs to be some additional enhancements and design measures taken to achieve that, and that would be essentially impossible to achieve that on every lab. So we agreed a sort of hierarchy of 3 performance criteria that would be provided in different areas. And then there was a sort of hierarchical layered approach to adding additional enhancements to then achieve that performance. So the lowest and least onerous vibration criteria that we agreed on was VCD, and that could be achieved at the first basement level where you see the letter A, and that was essentially provided purely through the stiffening of the structural design and the sort of organization of program. Then to achieve the next level up is where the letter B is, which is the VCG criteria. We had to introduce something called a keel slab. So I'll show you an image in a minute, but it's this sort of orange lump here, which essentially it's a 55-ton lump of concrete that is separate from the building structure. It's suspended on air springs, and as a result provides a very, very stable surface for experiments to then install their laser tables and experiments. And to achieve VCM, we then had to go a few steps further, and you can see it in this section here. We had to introduce a sort of box-in-box construction, and also shut down all services into the lab space at the time where they take the measurements to ensure that VCM was achieved. So this is a detailed close-up of that box-in-box construction. So essentially the experiment is set up in this lab here. And then this is the keel slab that sits on the air springs. And that third basement level, the basement level at the very bottom that I mentioned earlier, that was to contain vibration isolation equipment, that is this floor here. So it's purely there to accommodate these air springs and the keel slabs. And then we've got a secondary box enclosure that encloses the lab that is floating, so it's also isolated from the main building structure, and it just provides another level of acoustic separation from the main building, because sound is essentially an airborne form of vibration. So it's not just the surface that the experiment sits on that could affect the atom that is being analyzed, but also the air inside the room if there was noise in the room. So each of these labs has a vestibule right next to it, which will generally be connected to the lab. But then at the time when they need to take the measurements, they would fully shut down that inner box, shut down the services, and then from this vestibule, they would monitor the experiment and the data that was being recorded. I'm just going to hand this one back to Nick, who's going to talk a bit about the MEP provisions that were undertaken.
Yeah, thank you. So, I mean, one of the things we needed to do for the mechanical and electrical services to prevent any movement in the ducting or pipe work entering the building structure was install these high efficiency spring hangers, which you can kind of see in the photos there. So these hangers are available at 99% efficiency, so they can remove 99% of the vibration created by the service and prevent it from entering the structure. But they need to be very carefully selected based on the mass of the service they're trying to isolate and the movement. And most of the manufacturers of pumps and chillers and fans don't know the vibration movement of their plant, because it's not something they often have to provide. So one thing we had to do is we actually had to speak to manufacturers and go to their sort of warehouses and actually test and measure the vibration of their equipment, very similar specification to that we were going to be installing, and just so that we could get that information and get the hangers appropriately selected. So yeah, it was a very involved process, but I mean, it did mean that we had confidence that we weren't putting any vibration into the structure.
Yeah, and just to add to that as well, every single piece of pipe work or duct work in the building had to be fixed via one of these isolating hangers. So no services at all could be fixed straight into the building structure. And then these are just some pictures from construction. So the image on the left was it's essentially the full basement excavation. And they're just starting to cast the lowest raft slab. And you can see here this dark grey strip along the piles on the right. That's actually the depth of that lowest floor slab. And then on the right, you can see the first of the keel slabs going in. So they actually vary in size depending on the lab sizes. But they were essentially a combination of precast concrete and then in situ concrete toppings, because obviously they can't be moved and transported in their full form. And then this on the left is a keel slab at completion. So in this image, you can see the gap around the keel slab between the floor structure and the keel slab. So we had to leave a 50 mil gap to avoid there being any connection. And the keel slab in this image actually sits on steel shims, so it's obviously not yet floating. And the air springs will eventually sit, or they do now sit, in between the dwarf walls and the wings of the keel slab here. But as part of the project, because the department didn't yet know necessarily which physicists or research works would be in each of the laboratories, because some of these people were still being recruited, they decided to procure the air springs separately once the project was complete, because they are very specifically designed towards the type of work and the type of vibration that they're sort of wanting to isolate. So they have to be bespokely sort of specified and designed. And essentially we had to leave these dwarf walls with exposed rebar because different suppliers have different finishing requirements for the finishing of that dwarf wall level. So we just left it like this so that the client could then come back and complete it in line with their supplier requirements. And then the image on the top right just shows you some of the pumps and smaller equipment that the department moved in and uses as part of their day-to-day lab operation. And all of that had to be designed to sit on isolated slabs as well to minimize any vibration feeding back into the structure.
Yeah, I mean, that was one of the biggest challenges was, you know, once you've built the building, how do you stop scientists just moving in pieces of equipment? We've gone to all this trouble to make the building vibration free. How do you stop them just bringing in anything, any piece of equipment, and just like adding loads of vibration into the structure? So one of the things we did was we provided these little sort of user plant rooms effectively. So what you can see there is actual like lab equipment, you know, compressors and pumps that they use as part of their experiments. So we had to give them these little sort of grey spaces where they could put that stuff, and just that, you know, the inertia base, you can see there was actually really difficult, one of the most difficult things to design, because we didn't know what equipment they were going to provide. So all we could do was try our best to get like a one size fits all inertia base. But yeah, I mean, it seems to have been successful.
Yeah. And then the last image on the bottom right is just an image of that interstitial service floor that we were talking about. So you can see all the pipe work and duct work and everything is suspended by those isolating hangers. And then this is just, again, the final lab. So the image on the left is that box in box construction. So you can see in the foreground here, the double layer of doors. That's our two sort of skins of enclosure to the main lab space. And that's the surface of the keel slab popping up in the lab. And then the middle and right images are examples of that completed laser table and environmental control enclosure. And I think that is it from us. Thank you very much.
Thank you, Rebecca and Nick, for the presentation. And now we are in the Q&A session. If you have any questions, please feel free to post them in the Q&A session. And we currently have one question from Billy Duggan, who asked, did you provide radon protection in the fabric of the basement enclosure?
So I'm not quite sure what radon protection actually is. Could you clarify that, Billy, please?
If not, we can move to the
I guess
next one.
it's like probably just like a very firmly efficient insulation, is it? But so to answer that sort of question, no, we didn't provide any specifically enhanced thermal efficiency to the labs. I mean, they are in the basement anyway, like, so they were sort of protected from thermal heat losses and any solar gain that you might get, which made it a more stable environment anyway. And then one thing we did do was all of the laboratories were sort of notionally positively pressurized in terms of air, so and that was to stop any sort of uncontrolled air from the corridor coming in and compromising the temperature stability in the labs.
Yeah.
But we didn't provide any thermal efficient insulation over and above what you would normally provide.
Because the actually the sort of enhanced structural design as well hugely helped with this. So the having a 1200 mil thick lowest full slab and the pile wall, actually, because the basement was all excavated in one go, we had quite extensive piles. I think there were also like 1 meter in diameter, plus then your inner wall. So there was quite a lot of, I think, thermal insulation that was just achieved through the structure as well.
Thank you, Nick and Rebecca. We had another question from Sarah Darby. Please tell us about your post-occupancy evaluation. It would be good to hear about how building performs for the users in terms of energy use and etc.
Yeah.
Yeah, so we did do, sorry.
So it's fine, you start.
I was going to say, yeah, we did do some post-occupancy evaluation, and yeah, we sort of skimmed over energy targets a little bit, actually. So that's a good point. I mean, obviously, buildings do have energy targets, and this type of laboratory where you've got super tight environmental control that require a lot of air, obviously consume a lot of energy. I mean, one thing to note is that actually that kind of energy consumption isn't regulated, if that makes sense. So you've got Part L of the building regulations, which stipulates how much energy you can use. But if you're using what's called a process load, which is something for a specific type of scientific research, the Part L calculations actually kind of overlook that and say, okay, well, that's over and above what you're normally doing, so don't worry about that. But obviously, we still wanted to make the building as energy efficient as possible. So we did include some ground source heat pump technology in the building. And we were able to meet the building regulations requirement. In the post-occupancy evaluation we did, funnily enough, most of the stuff that we got back was actually in the offices, not in the labs. I think the experimental physicists were happy they could do their research, and actually it was the theoretical physicists who were sat in an office who notice things, I don't know, a temperature change. So most of the post-occupancy evaluation was like, oh, my office is cold, my office is hot, my office is drafty. And all the post-occupancy evaluation will always focus on that kind of thing, really, because that's the sort of thing people notice. So that's the bit.
Yeah, I was going to say that I think we got a hugely successful response with regards to the offices and the collaboration areas. So in fact, when the building first opened, people from other departments would come and start using the atrium to the point where they sort of had to be a bit more controlling and restrictive about who could use the atrium. And I think, I mean, people just generally commented on things like, that it's really improved their sort of sense of well-being and, their experience at work, of being at work. So they've really enjoyed coming in now. And I think one of the other reasons why there's sort of more of a response on the office side was because I think until people have a new environment, they don't really know that their environment isn't that great. So, people were in cellular offices and they are now in cellular offices, but the component that was missing was that collaborative, interactive environment that sort of ties it all together. And, without having experienced it, I think a lot of people didn't know that that could be something that they are missing. And I think on the labs as well, the labs were purposefully, there's only a few of them that were actually occupied within the first year of completion, because the department specifically wanted to use those labs as a way and a tool to recruit new researchers. So you know, a lot of the labs will be occupied over time, but will just take longer to actually get people into them and get them fully using them. So I think there's just naturally going to be a slower feedback on that.
It's a good question though, and post-occupancy evaluation is really important to do. And on this building, we did, you know, we mentioned that we got some negative feedback on the office environmental control, but you know, actually a lot of it was just a basic sort of programming error on the BMS, on the building management system. And actually, we went and made a few changes, and then got some more feedback, and it was really positive that we'd made an improvement. So it just shows it is really worthwhile to go in and ask people, how is the building performing, and get that in feedback. And usually it's quite an easy fix. So yeah, it's a really important thing to do.
Right. The next question is from Valentina. Thank you for the interesting presentation. The question is about the environmental control design in the enclosure. Do you know what is the airspeed within the enclosure? What about the air pressure? Were there any requirements from the client on this?
Yeah, so they did raise the question of air velocity, and again, because the experimental was so delicate, they didn't want a high airspeed within the enclosure. I know I sort of mentioned 80 air changes an hour, and like a high percentage of the air going to the enclosure, which sounded a lot, but you can sort of see on the image on the right, we had these quite large diffusion type grills that actually introduced the air at low velocity. So the air velocity was only designed at about 0.1 meter a second, so still quite slow. So you couldn't feel a draft or anything in there if you were to put your hand in there. And there was quite a big gap, and you can sort of see in the enclosure, quite often they have the panels open and the enclosure doesn't quite fit around the table. So it wasn't like a high air pressure. Again, the air had plenty of room to escape. So there wasn't a target on air pressure either.
Okay, I think we still have time for one or two more questions. So the next question is, once those air springs below the kill slabs that are specified for the current research requirement installed, will they be changeable to adapt to the potential change of research requirement in the future?
Yeah, absolutely. And that was the primary reason for providing a full additional basement level below the labs to contain those keel slabs and air springs, because in theory you could have just dug local holes below each labs to hold the keel slab, but having a full floor means that they're fully accessible, and the elevator goes down to that level, so that allows for easy installation, replacement and maintenance of those air springs in future.
Okay, we still have a couple more. What simulation program did you use for heating and cooling loads and HVAC early design components?
So we modeled the building using IES, thermal assessment software, and also that's how we used our energy compliance calculations. And then in the early design stages of the closed control system, I mean, we didn't really use anything other than just sort of, you know, mechanical design process and calculations. But that was why it was so critical, really, that we built the mock-up, because it's such a difficult thing to simulate in computer software. You know, are you going to achieve plus or minus 0.1? Because all computer software will ever do is just like a steady state heat loss. And so, of course, if you put more heat in, then the heat's going to go up, because it's just looking at things instantaneously. So you'd never get a picture of what's actually happening from like 1 second to another. So that was the real reason why we needed to build the mock-up.
Okay, the next question. How did a single stair core work with fire escape strategy from 5-story deep basement?
So we didn't have one, we actually had 3 stairs. So I'll just hold on. I'll just flick back to basement floor here. So we've got 1 stair core here, and then 1 on the right side here. And then this 3rd stair at the bottom was more of an accommodation stair that was sort of read as an extension of the atrium. So that was not officially an escape stair, but obviously used to improve circulation in day-to-day.
Great. And the next one is, did you use natural or mechanical ventilation for the lower floors? Good ventilation will avoid radon concentrations.
We did, the whole building was mechanically ventilated. So in the basement, obviously that was part of the sort of air conditioning system. And I mean, it was in the basement, so we didn't have opportunity to naturally ventilate very easily. And then in the offices, we mechanically ventilated mainly because of the acoustic targets, as Rebecca mentioned. The theoretical physicists, they wanted a very quiet environment so they could concentrate on their equations. And the location of the building was right next to a busy road. So if you'd had a natural ventilation through opening windows, you would have had, you know, very difficult acoustics to overcome. So again, the whole building really lent itself to mechanical ventilation.
Yeah, but there was a request by the theoretical department to have operable windows in the offices just for user comfort. So there are opening windows that are then connected to the ventilation system to shut down the ventilation system automatically if they were to open those windows.
Okay. Okay, great. There's one more question from Sarah Derby. How did the energy used error compared with the design estimate?
So yeah, we did some seasonal commissioning on the building, and at first it was considerably more than we estimated, but that was because mainly of some a sort of a different subject really, but it was a bit of the main plant design. We had two very large chillers and two very large boilers, and actually the problem with doing that is, rather than having multiple pieces of plant, is it's difficult to have flexibility to meet mid-season loads in sort of when it's not extremely hot or extremely cold. You've got one big chiller or one big boiler trying to do a very small load, and actually then it means it's operating inefficiently. So that was the main reason that we had a difference to our estimated energy usage, but we managed to make some changes to the system. We added in some buffer vessels, and that really smoothed it out. So again, it just shows the sort of power of doing post-occupancy evaluation and seasonal commissioning, because you can discover these things and make changes and get the building to perform, you know, as best as it can to save energy as much as you can.
Great, great. Thank you once again, Rebecca and Nick, for the wonderful presentation and brilliant answers to the questions. We got a lot of questions approaching the end of the Q&A session. So I think that's all for today. Please register our other webinars if you're interested. And I'm looking forward to seeing you all again.
Thank you very much.
Thank you for having us. Thank you. Cheers.
Thank you.